Picture this. You walk into an old stone cottage or a medieval farmhouse on a freezing winter morning. Outside, it's below freezing. Inside, the air feels steady and comfortable. You don't need the heating on full blast. The walls themselves seem to hold the warmth from yesterday's fire. Now step into a modern new-built house on the same winter morning. The thermostat is fighting hard. The rooms feel chilly near the windows and walls, even though the heating has been running all night. By afternoon, the sun hits one side and the house overheats, forcing you to open windows or crank the air conditioning. What changed? For hundreds of years, builders routinely constructed homes with walls 3 feet thick, sometimes more. Stone, brick, cob, rammed earth, or timber framed with thick infill created massive barriers between the inside and the outside world. These walls weren't just structural. They were thermal batteries, sound barriers, fire shields, and security features all in one. They kept houses cool in summer and warm in winter with far less fuel than we use today. Then, somewhere along the way, we stopped. We started building with 2x4 timber frames, thin brick veneers, insulated cavity walls that are often only 30 to 40 centimeters thick in total, and lightweight materials that go up fast and cheap. The result? Homes that require constant mechanical intervention to stay comfortable. Homes that swing wildly in temperature. Homes that feel noisy, fragile, and expensive to run. Why did we abandon 3-foot walls? Was it progress? Cost? New technology? Or did we lose something valuable in the rush to build faster and cheaper? This is the story of thick walls, what they actually did, why they worked so well for centuries, why modern building largely abandoned them, and whether bringing back some of that old wisdom could solve problems we face right now with energy costs, climate extremes, and uncomfortable homes. Walk through almost any new housing development, and you'll notice something odd. The walls feel thin. Tap them, and they sound hollow. On a hot day, the sun beats through them quickly. On a cold night, the cold radiates inward. People complain about cold spots, drafts near windows, and rooms that never quite feel right, no matter how much the heating or cooling runs. This isn't just perception. Modern lightweight construction has traded thermal mass for speed and low material cost. A typical modern cavity wall might have an outer brick skin, a cavity with insulation, and an inner block or plasterboard lining. The total solid mass is low. Heat moves through it relatively easily once the insulation is overcome. The result is buildings that respond quickly to external temperature changes. That sounds efficient in theory, but in practice, it means the heating system has to fight the weather constantly. In summer, the same thing happens in reverse. Thin walls let heat in fast, forcing air conditioning to work harder. Energy bills reflect this. Many modern homes use far more energy for heating and cooling than older thick-walled buildings of similar size. The constant cycling of mechanical systems also creates noise, dry air, and higher maintenance costs. When the power goes out during a storm, these homes can become uncomfortable within hours. Our ancestors rarely faced this problem. Their thick walls acted as a buffer. The mass of the wall absorbed heat during the day and released it slowly at night. Temperature swings inside were dramatically smaller. People stayed comfortable with less fuel, wood, coal, or even just body heat and cooking fires. 3 feet is roughly 90 centimeters. That's thicker than many modern load-bearing walls. In historical building, this thickness appeared in many forms. Solid stone walls in cottages and farmhouses across Britain, Ireland, and parts of Europe. Thick brick walls in townhouses and warehouses. Cob or earth walls in parts of England, Wales, and other regions where suitable soil existed. Rammed earth or adobe in hotter or drier climates. timber-framed buildings with very thick wattle and daub or brick infill. These walls were not built for show. They served multiple critical functions at once. Thermal mass was the primary benefit. Stone, brick, and earth have high specific heat capacity. They absorb heat slowly and release it slowly. On a sunny day, the wall absorbs warmth from the sun and from internal activities. At night, it radiates that stored heat back into the room. The indoor temperature stays remarkably stable, even when outdoor temperatures swing 15 or 20 degrees. Insulation through mass worked differently from modern insulation. Modern insulation traps still air. Thick masonry walls reduce heat flow through sheer volume and the time it takes for temperature changes to travel through the material. When combined with lime plaster and good detailing, they managed moisture well too. Structural strength and longevity came almost for free. A 3-foot stone or brick wall could support heavy loads for centuries. Many buildings with walls this thick are still standing and habitable after 400 to 600 years. They resist fire better than thin timber frames. They provide excellent sound insulation between rooms or from outside noise. Security and defense mattered in earlier centuries. Thick walls made forced entry difficult and offered protection during conflicts. Moisture management was handled naturally. Traditional thick walls built with lime-based materials were breathable. They allowed moisture to move through rather than trapping it, reducing mold and decay problems that plague many modern sealed buildings. These walls were not primitive. They represented sophisticated vernacular engineering, local materials used with deep knowledge of climate, physics, and long-term performance. People who live in well-preserved old stone or cob houses often describe a unique quality of comfort that modern homes struggle to replicate. The air feels different. Temperature changes are gradual. There are fewer drafts and cold spots. Sound is muffled. In summer, the interior stays cooler without air conditioning. In winter, it retains heat from a fire or even just daily activity. This comfort comes from physics. Thermal mass smooths out temperature fluctuations. A 3-foot wall has enormous capacity to store and release heat. It acts like a giant battery. Modern thin walls with high insulation values, but low mass, do the opposite. They let the interior temperature track the exterior more closely once the insulation's resistance is overcome. Studies on thermal comfort consistently show that people feel comfortable across a wider range of air temperatures when surrounding surfaces, walls, floors, are at a moderate temperature. Thick walls keep those surfaces closer to the desired indoor temperature. Thin walls can leave surfaces colder or hotter, making the room feel uncomfortable even when the air temperature is correct, according to the thermostat. Old houses with thick walls also tended to have better natural ventilation strategies. Small windows, shutters, and strategic placement allowed controlled airflow without losing too much heat. The mass of the walls compensated for periods when windows were closed. The move away from thick walls accelerated during the Industrial Revolution and exploded in the 20th century. Several powerful forces drove the change. Speed and cost of construction became dominant priorities. A timber-framed house with thin walls and modern sheathing can be built in weeks rather than months. Materials are lighter, easier to transport, and require less skilled labor. Developers and builders responded to market pressure for faster, cheaper housing. New materials and manufacturing made thin construction possible at scale. Mass-produced bricks, concrete blocks, steel framing, plywood, and later insulation boards allowed walls to be assembled like components rather than built as massive monolithic structures. Central heating and later air conditioning changed the equation. When every room could be heated or cooled mechanically at the push of a button, the need for the building itself to moderate temperature decreased. Builders and owners began to rely on machines rather than the fabric of the house. Changing building codes and standards focused on measurable insulation values, R values or U values, rather than thermal mass. Codes rewarded adding insulation to thin walls more than building massive ones. Energy calculations often treated mass as secondary or ignored its benefits in dynamic conditions. Aesthetic and cultural shifts played a role. Modernist architecture celebrated lightness, openness, and new materials. Thick stone walls felt old-fashioned or associated with rural poverty in some cultural contexts. Thin walls allowed larger windows and more modern appearances. Urbanization and standardization pushed construction toward repeatable, factory-influenced methods. 3-foot walls are difficult to standardize across different sites and climates compared with lightweight framed systems. Earthquake engineering in some regions favored lighter structures that could flex rather than rigid heavy walls, though well-built thick masonry can perform well with proper detailing. The combination of these factors made thin walls the default for most new housing by the mid to late 20th century. The old knowledge of building with mass was largely lost from mainstream practice. The consequences of abandoning thick walls are visible today in energy consumption, comfort complaints, and building longevity. Energy use for heating and cooling in the residential sector remains high in many countries, despite better insulation standards. Much of that energy goes into overcoming the lack of thermal mass, constantly reheating or recooling air that escapes or changes temperature quickly. Comfort complaints are common in new homes. People describe rooms that feel cold even when the thermostat says 21 degrees Celsius, or stuffy and hot in summer. Thin walls transmit more noise. They offer less protection during power outages or extreme weather. Durability has suffered in some cases. Lightweight construction can have shorter expected lifespans for certain components. When problems arise, moisture ingress, structural movement, repairs can be more invasive because there is less robust mass to work with. The environmental cost is also significant. Manufacturing and transporting lightweight materials, installing mechanical systems, and then running those systems for decades adds up. Thick walls built with local stone or earth have very low embodied energy and can last centuries with minimal intervention. Thermal mass works because of specific heat capacity and the time lag effect. Materials like stone, brick, and earth require a lot of energy to change temperature. Once warm, they stay warm for a long time. A 3-foot wall has a huge volume of this material. Heat travels slowly through thick masonry. There is a time lag between when the outside temperature changes and when the inside surface responds. In a well-designed, thick-walled building, the interior can stay comfortable during the hottest part of the day because the wall is still releasing heat absorbed the previous evening or from internal sources. Modern insulation is excellent at slowing heat flow, but it has almost no capacity to store heat. A thin insulated wall lets very little heat through, but once heat does get in, or the interior heat is lost, there is little mass to buffer the change. The room temperature swings more. Passive solar design principles recognize this. Many high-performance buildings today deliberately incorporate thermal mass, concrete floors, thick masonry walls, or water containers, precisely because mass stabilizes temperature and reduces mechanical energy demand. These are modern rediscoveries of principles that old builders understood intuitively. Real-world performance often favored thick walls more than simplified calculations suggested. In variable climates with cold nights and warm days, or hot days and cool nights, mass shines. It stores the cool of the night for the day ahead, or the warmth of the day for the evening. Thin, highly insulated walls can overheat in summer if solar gain is not perfectly controlled, and they cool down quickly when heating is off. Moisture behavior is another area where traditional thick walls often performed better. Lime-based plasters and mortars on thick masonry allow the wall to breathe. Moisture can enter and leave without causing damage. Modern impermeable systems sometimes trap moisture, leading to hidden decay or mold. Sound insulation is dramatically better with thick, solid walls. 3 feet of stone or brick provides excellent acoustic separation that thin-framed walls struggle to match without additional expensive layers. Fire resistance is superior. Thick masonry walls contain fire far better than lightweight construction. Security and storm resistance are higher. Thick walls simply take more effort to breach and provide better protection against wind-driven rain or debris. Interestingly, some of the most advanced green building approaches today are rediscovering the value of thermal mass. Passive house standards sometimes incorporate significant mass. Earthships and other off-grid designs use thick earth or tire walls for thermal mass and insulation. Rammed earth and straw bale buildings with thick walls are gaining popularity for their comfort and low environmental impact. Some high-end eco-homes deliberately use thick stone or concrete walls, combined with excellent insulation and airtightness. These projects show that mass and modern performance are not mutually exclusive. You can have thick walls with modern insulation strategies, good detailing, and mechanical systems that work with the mass rather than against it. The question is why this approach remains rare in mainstream housing when the benefits are clear. Even if we cannot return to building every new house with 3-foot solid stone walls, there are practical takeaways. Incorporate thermal mass where it makes sense. Concrete floors, internal masonry walls, or thick external walls in key areas. Design for time lag effects rather than just steady-state insulation values. Prioritize breathable materials and good moisture management over complete sealing in many climates. Consider hybrid approaches, thick mass walls where durability and comfort matter most, combined with modern insulation and detailing where needed. Value longevity and low maintenance over initial speed and lowest upfront cost. Recognize that older thick-walled buildings often have inherent advantages that can be enhanced rather than stripped out during renovation. For existing old houses with thick walls, the best strategy is often careful repair and enhancement rather than replacement with modern thin systems. Keeping the mass and improving insulation, ventilation, and heating controls usually delivers better comfort and lower running costs. The shift away from thick walls was driven by real pressures: rapid urbanization, the need for affordable housing at scale, new manufacturing capabilities, and the promise of mechanical systems that could solve comfort problems. In many ways, it was understandable progress, but we may have overcorrected. We optimized for speed, cost, and measurable insulation values, while undervaluing dynamic performance, longevity, and the multifunctional benefits of mass. We created buildings that require constant energy input to stay comfortable, instead of buildings that help maintain comfort with less intervention. As energy costs rise, extreme weather becomes more common, and we face pressure to reduce carbon emissions from both construction and operation. The old approach looks increasingly attractive again. 3-foot walls were not built because people were ignorant. They were built because they solved multiple problems simultaneously with available materials and knowledge. We stopped building them primarily because other priorities took over, not necessarily because better solutions had been found for every aspect of performance. The question, why did we stop building homes with 3-foot walls, leads to a deeper one. What do we actually want from our homes? Do we want the cheapest possible construction that meets minimum code? Or homes that stay comfortable with minimal energy input, last for generations, feel solid and quiet, and work with the climate rather than fighting it constantly? Thick walls were one answer to that deeper question. They were not perfect for every situation or climate, but they represented a proven, low-tech, high-performance approach that served people well for centuries. Modern technology gives us options our ancestors did not have, better insulation materials, more efficient heating systems, smart controls. The opportunity now is to combine the best of both worlds, the thermal stability and durability of mass with the precision and efficiency of modern systems. Some builders and homeowners are already doing this. The results? Comfortable, quiet, efficient homes that feel substantial suggest we may have thrown out valuable knowledge along with the old methods. We stopped building homes with 3-foot walls mainly because we prioritize speed, standardization, and mechanical solutions over the inherent performance of massive construction. The change brought real benefits in construction speed and initial cost. It also created ongoing costs in energy, comfort, maintenance, and environmental impact that we are still paying today. The old, thick-walled houses were not primitive. They were sophisticated responses to real conditions using the best available materials. Their thermal mass, durability, and multifunctional performance delivered comfort and resilience that many modern homes struggle to match without constant mechanical assistance. Bringing back some of that wisdom does not mean rejecting all modern progress. It means recognizing that mass has value, that buildings can moderate their own environment, and that longevity and low operational energy are worth designing for from the start. The next time you stand in an old stone house that feels comfortably warm in winter or cool in summer, with almost no heating or cooling running, ask yourself, what are these thick walls doing that my modern walls are not? The answer is not magic. It is physics, material science, and centuries of accumulated practical knowledge. We stopped building 3-foot walls for understandable reasons. But the problems those walls solved have not gone away, and in many cases, they are getting worse. Perhaps it is time to remember why our ancestors built them so thick in the first place. If this video made you look at old buildings differently, or question how we build today, give it a like and share it with someone who loves old houses or is planning a new one. Subscribe for more explorations of forgotten building wisdom that still has power to make our homes better. The knowledge is still there in the walls that have stood for hundreds of years. We just have to be willing to learn from them again. Thanks for watching. Stay comfortable, however thick your walls may be.